Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Andrei Stolov, member of technical staff, OFS, of Furukawa Company in Avon, Connecticut, USA, who will be presenting his paper on acrylate-based specialty optical fiber coatings for harsh environments. Andrei Stolov received his PhD degree in physics from Kazan State University in Russia, where he became a senior research fellow in the Department of Chemistry. He subsequently held positions as a visiting scientist at RUCA University in Antwerp, Belgium, and as a postdoctoral fellow in the Polymer Science and Engineering Department at the University of Massachusetts, Amherst. In 2000, Andrei joined Lucent Technologies, now OFS, in Avon, Connecticut, as a member of technical staff, where his focus has been the development and characterization of polymer coatings for specialty optical fibers. Dr. Stolov has authored more than 100 publications in fields of molecular spectroscopy, polymer science, and photonics. Andrei, we welcome you to present at today's IWCS webinar series event.
Thank you very much for the presentation, for introducing me. So it's a great pleasure and a great honor for me to give you a presentation on acrylate-based specialty optical fiber coatings for harsh environments. First of all, why are we interested in harsh conditions? That is because more and more often optical fibers are being used as such conditions as the one shown on this slide. In this picture you can see an optical fiber which is used downhole for distributed temperature sensing, and here it can meet high temperature, high pressure, high humidity, presence of hot steam, presence of aggressive chemicals, mechanical interactions, presence of hydrogen, may be the combination of the above. And the goal for us as optical fiber manufacturers is to produce such fiber for which we will achieve minimum added optical loss during the usage time, ensure that there are no breaks in the fiber, and extend the lifetime of this fiber this way as much as we can. Now, what can fail in the fiber and what are the failure criteria? It could be, for instance, the loss of strength by a certain amount of gigapascals. It could be added attenuation by a certain amount of dBs per kilometer. It could be something more simple. For instance, the fiber starts sticking to the hardware, or the coating is outgassing. And in any case, we should say that always the failure criterion is application driven. It depends on the application. Take the same fiber and use it in two different applications. For instance, one application may be in medical area, the other in geophysical. You will have a different list of the requirements, different list of the failure modes, and therefore a different list of the failure criteria. Now, if the failure criterion is defined and if the fiber is used at elevated temperatures, then we can start speaking about what is the upper use temperature, what is the continuous use time, and both of them depend on the failure criterion, and also they are related to each other. I'm going to explain it in a while. Molecular-wise, there are four main chemistries which are successfully used for coating optical fibers. Most common are acrylate coatings. All these formulas, of course, are oversimplified. Less common are silicones and polyimides, and even less common, but more and more popular recently, are so-called hybrid formulations, which are hybrids between organics and inorganics. They have a silica-type backbone, Si or Si, from which some organic radicals are evolving. For instance, acrylate groups can be included in these organic radicals. Most common telecom-grade fibers have dual acrylate coatings with a soft primary with a Young's modulus about 1 megapascal and a hard secondary coating with a Young's modulus about 1 gigapascal. The role of the primary coating is to cushion possible microbends. Such coating typically is rated to temperatures about 85 degrees C, which follows from the data sheets of most producers of optical fibers. On the other end, we have polyimide coatings. Polyimide coatings have very high thermal stability. Such fibers can be continuously used up to 300 degrees C. What is of interest for us in this presentation is some intermediate options. Can we modify acrylate coating to get something with higher thermal stability? For instance, we can, instead of a dual coating system, use a single coat. We can utilize a silicone as a primary coating. We can try a hybrid organic-inorganic material as a single coat. So there are different strategies, and for us, the main questions were, how high can we go in temperature if we do such modifications? And the second question, do we sacrifice anything? Are there any side effects if we improve the thermal stability of the coating? Should we sacrifice any important property of an optical fiber? So for this study, we selected a long list of coatings. Most of them are commercially available, so we got them from different manufacturers. There is a list of primary coatings from P1 to P9. We also used two silicone coatings, Si1 and Si2. These silicone coatings are UV curable. They have acrylate groups in them. There is a series of secondary coatings from S1 to S5 and a list of monocoats from N1 to M4. Also, a hybrid formulation was utilized once. It was used as a monocoat. All these coating formulations have different chemistry. Some of them contain urethane, which is marked in the second column by U. Some of them do not have urethane, which is marked by N. In two cases, we added a cross-linker, CR, so primary coatings P6 and P7 were made out of P2 by adding 10 or 20% of a cross-linker. Primary coatings P8 and P9 were formulated ourselves. For this, we used two different polybutadiene-based oligomers, one with urethane and the other without urethane. These are the only coatings that we formulated ourselves. Also, in two cases, we added an adhesion promoter. So we added it to a silicone coating Si2, and we added to a monocoat M3. The third, fourth, and fifth column of this table shows the storage modulus at room temperature, equilibrium storage modulus, and the glass transition temperature. Briefly looking at these columns, you can see a very strong variability of properties, so it was interesting for us. Do these properties cause any effect on thermal stability or maybe on other properties of optical fibers? Primary and secondary coatings were combined together, so we drew a few fibers with dual coatings, and this is shown on this table on the left. The coatings DA1 up to DA9 are dual coatings. Two fibers also had dual coatings, but they belong to sort of a special class. They use silicone acrylate as a primary coating, Si, HTA1 and 2. And there is a series of fibers we drew with monocoats, SA1 to SA4, and also a hybrid formulation was used as a monocoat. On the right part of this slide, you see the waveguide we selected. So all these coatings were applied on a fiber with a graded index 50 micron core, 125 micron cladding, numerical aperture 0.2. Why we selected this waveguide? Because these fibers are commonly used for distributed temperature sensing. It is important to note that among these coatings there are two, DA1 and DA2, from the top of the list, which can be qualified as telecom-grade coatings. So we use them as a benchmark, and the rest of the coatings are positioned as potentially higher temperature coatings. So we drew these fibers and we tested them using an extensive test program. The first half of the test was so-called common tests. So they are relevant, for instance, to telecom fibers. And the first test in this series is the coating strip force. If you have a fiber with an acrylate coating, then ideally you should be able to strip this coating mechanically without breaking the rest of the fiber. For telecom-grade fibers, there is a specification. The strip force must be in the range between 1 and 9 newtons. So for all the dual coating systems, we see that the strip force falls in this range. For single-coated fibers, there may be some problems. Really, the strip forces are significantly higher. And for two of the coatings, at least some of the data points fall above 9 newtons. And indeed, the coatings SA4 and hybrid coatings are hard to be removed from the rest of the fiber without breaking the glass. So we notice advantages and deficiencies of different properties, and then at the end we will summarize them all together. Another important property, delamination resistance. This is relevant to dual coatings only. If we indent an optical fiber by applying a force above it, then sometimes we can see that a delamination developed. Delamination between the glass and the primary coating. The higher is the force which is needed to create this delamination, the better for the fiber, the higher is the delamination resistance. So the delamination resistances that are obtained for dual-coated fibers are shown here. The clear winner in this test is a fiber with the telecom-grade coating DA1, and there is a fiber with the coating DA9 with the lowest delamination resistance among this series. Microbend sensitivity. For this, we used a standard procedure. A fiber was displayed on a rubber pad, closed with a mesh and loaded from the top. Simultaneously, we measured the induced optical losses, and the result obtained for the 2.5 kilogram optical loss, for 2.5 kilogram load force, are shown on the right part of this slide. So here we have the added optical loss. As expected, dual coatings exhibit smaller added optical losses because they have soft primary coating. It cushions the microbends. Surprisingly for us, we see that fibers with silicone primary coating, although silicone is soft, exhibit somewhat higher added optical loss. And of course, single-coated fibers exhibit on average higher optical losses. Another surprise for us was a relatively low difference between the dual coatings and single coats. Single coats do not have this cushion layer. However, the differences may be 1.5, 2 times only between dual and monocoats. We determined the strength of all these fibers using two-point bend test technique. All the fibers are stronger at least than 4 gigapascals. Most of them are stronger than 5 gigapascals. And applying this test at different strain rates, we also determined the stress corrosion parameter, the N values. There is an industrial standard for the N values. They're supposed to be above 18. And we see that for all the drawn fibers, the N values are indeed above 18. Some of them are very high, but for some of the coatings like DA4, DA6, they are dangerously approaching the number of 18. So that was the end of the standard test program. Now I'm switching to the high temperature and harsh test program. If we're talking about thermal stability, what is it? it can be defined differently, and as I told in the very beginning, for each application, it depends on what this application is. So here we applied an extensive test program. First of all, the fibers were tested using dynamic thermogravimetric analysis in air. Then we applied dry aging in the air and in nitrogen. Then the fibers were exposed to autoclaving. Then we used high temperature and high pressure aging of fibers in water and a cable gel. We also tested fibers for their hydrogen evolution. And we also tested another extreme, low temperatures region. We immersed fibers in liquid nitrogen. I'm going to describe you these results one by one. First of all, an important failure mode at elevated temperatures is thermal decomposition of the coat. And this can be followed using thermogravimetrical analysis. In this method, a sample is heated from room temperature to some high temperature, and at a certain point we can see that the weight of this sample is getting lower due to thermal decomposition. So we can follow thermal decomposition using thermogravimetry, and the question is, what should we take as a failure criterion? Since the actual failure of the optical fiber depends on the application, and since we do not know in the beginning what the application of this fiber will be, we are free to select an arbitrary number. So we decided, let's take 25% weight loss as the failure criterion. So we assume if at an elevated temperature the coating loses 25% of its initial weight, that is the end of the lifetime for this coating and for this fiber. The TGA experiments can be performed at different heating rates, and using some equations we can determine the times and the temperatures that correspond to this 25% weight loss achieved by the coating. This data then can be plotted in Arrhenius coordinates and extrapolated to other times and temperature conditions. On this slide, on the left-hand part, you can see examples of the TGA curves obtained for different coatings, and you can see that these curves are different. They can be used as a fingerprint for different coatings. And on the right-hand side, there are examples of the data that we obtained using the TGA method. So they correspond to 25% weight loss criterion, and the x-axis is the use temperature, and the y-axis is the continuous use time. These two parameters are correlated to each other. I'm going to explain it in some details a little bit in a couple of slides. The important is that from these dependencies, we can determine the upper use temperature for individual coatings that correspond to the 20-year lifetime. And these data are shown on this slide. So for all 16 fibers, we have the upper use temperatures that are obtained by extrapolating our TGA data. The first two columns correspond to the telecom-grade coatings, DA1 and DA2. And you can see that these numbers are grouped around 85 degrees C. That agrees well with an official rating for telecom-grade coatings. Indeed, telecom-grade coatings are typically rated to be good up to 85 degrees C. And that justifies well our failure criterion selected for the TGA 25% weight loss. Now, if we look at the highest numbers here, the highest numbers are around 130 degrees C. The absolute winner in this test is a fiber that has a silicone primary coating, but there are also other fibers, SA2 and 3, for instance, or even DA3 fiber with a dual coating, which have pretty high upper use temperature. What is important for us is that we are not getting very high numbers. The highest numbers we can get is about 130 degrees C. Of course, we didn't test all acrylate materials as potential coatings for optical fibers, but we tested a lot, and it is a feeling that using acrylate-based materials, we cannot get the upper use temperature much higher than 130 degrees C. So if we take these numbers, 85 for a standard telecom and 130 degrees for the highest, the difference between them is 45 degrees C. So this 45 degrees C is probably the maximum improvement we can get by modifying the chemistries of the acrylate-based coatings. The yellow column on the right corresponds to the hybrid formulation. We expected much more from it, but it's not outperforming even some of the dual coatings. The fibers, one of the examples of the correlation obtained from the TGA data is shown here. So that is the curve for one of the coatings with the x-axis equal to use temperature, and the y-axis is the continuous use time. So for this coating, the 20-year lifetime, according to our TGA criterion, corresponds to 130 degrees C. Now, can this fiber be used at higher temperatures than 130? Yes, it can be used, for instance, at 300 degrees C, but for a shorter time, about 1 hour. Unfortunately, this comparison shows that there is a big room for speculations. Depending on the failure criterion and depending on the usage time, we can say for the same coating that it is good up to 130 degrees C, or it is good up to 300 degrees C, or to any other temperature. And unfortunately, some manufacturers of optical fibers can say that this coating is good up to 130 degrees C, and the other manufacturer will give a different number. Once again, it is a room for speculations. Ideally, we should provide here what was the criteria and what was the continuous use time that is in mind. So these fibers were then aged at different conditions. This slide shows one of the examples. Dry aging at 150 degrees C for 28 days. What we observe, we see some discoloration, stronger for standard telecom fiber DA2, less for fiber with silicone primary coating, and in one case we observed cracking. This case corresponds to the hybrid formulation. We measured the strength of the fibers before and after the aging using two-point bend test technique, and we see that all the fibers are pretty strong after this aging. So this discoloration and possible shrinkage didn't cause any adverse effect, including the fiber with the hybrid coating. The fibers were exposed to autoclaving. It is really a harsh environment because the temperature is pretty high, 132 degrees, and we have hot steam. The autoclaving time was about 3 hours in total, and here we see some differentiation. The fibers with coating DA8, SA2, and SA3, and also fiber with the hybrid coating, for these fibers we see a significant strength reduction. So we notice these coatings are not behaving very good in humid environments, but for the rest of the coatings, the results are pretty good. Really harsh testing. Short pieces of fiber can be immersed in a fluid like a cable gel or water. Then we can apply a high pressure up to 2000 psi, and we also can place this in a high temperature oven, so we can increase the temperature to a values 200 degrees C or even higher, and that would mimic a real downhole application of an optical fiber. I'm going to show you some of the examples. The fibers were aged at 2000 psi in water, and the temperature of water was 100 degrees C. What happens after that? We do not see significant discoloration, and two fibers with coatings Da2 and silicone HTA, they look the same as they looked before the aging. One fiber with a hybrid coating cracked. If we use a high temperature water, 160 degrees C, then we find some discoloration, more cracking for the hybrid coating. In addition to discoloration, we can notice shrinkage of the coating. It means that the coating material starts moving, diffusing into surrounding water. If we further increase the water temperature, what we'll see? We see that all the coatings 100% dissolved in water, and the leftover is just bare silica glass. We measured the strength of these fibers before and after aging at different conditions in water, and these are a few examples. After exposure to 100 C water, we see that some of the fibers are getting weaker, and these results match well with what we get with the autoclave experiment. When water temperature goes to 160 degrees C, then all the fibers drop in strength. But there are still a few fibers which maintain pretty strong, higher than 3 gigapascals, and among them there are fibers with silicone high temperature acrylate coatings and some other fibers. If instead of water we use a cable gel, what's happening? We use the cable gel, immersed fibers in it, applied high pressure, and the cable gel temperature was 160 degrees C. Then most of the fibers we observe do not lose their strength, but there are two exceptions. There are two fibers where the primary coating was based on polybutadiene oligomers. These oligomers swell very strongly in the cable gel, and the fibers, the coatings became loose tubes, easily removable from the fibers. So definitely such type of primary coatings are incompatible with usage in a cable gel. Hydrogen evolution was tested for some of the coatings, and the results are shown here. The highest number we see is 0.7 microliters per gram. Is it a high number or a low number? So notice that this number corresponds to a fiber with a silicone primary coating. So there is a rumor that silicone coatings generate lots of hydrogen, and this is really true for thermally curable RTV type silicones. And at the bottom of this slide, you can see the number. 100 microliters per gram is typically evolved, milliliters per gram is typically evolved from RTV type coating. So all these fibers can be considered as evolving just a little hydrogen, and this shouldn't be a problem. And for two of the coatings, we see that even no hydrogen was generated during the testing. Low temperature properties of the fibers. A fiber coil can be immersed in liquid nitrogen. Then, due to a mismatch between the CTEs of the coating and the glass, we expect seeing microbends. Then, if we have this fiber in line with the optical measurement bench, we can register added optical loss due to these microbends developed at low temperature. These results are shown on this diagram. So there are some coatings for which the microbend-induced effect at liquid nitrogen temperatures is pretty high. The highest number we get is about 25 dB per kilometer. It is for the coating Da5, and again we see that for the telecom grade coatings Da1, Da2, the effect is pretty small. So all these properties, all these observations were combined in a huge table, And from this huge table, we wanted and created a smaller table, which lists all the coatings that we trialed. And once again, most of the coatings are commercially available. So we placed deficiencies only in this table. The blue column corresponds to deficiencies observed at room and lower temperature. The purple column corresponds to deficiencies observed at higher temperature sites in harsh environments. Nothing in a certain cell means that there are no or almost no deficiencies. So the best performing coatings at room temperature end are telecom grade coatings DA1 and DA2. All other coatings have some deficiencies. For instance, strong added loss at low temperatures, or they're microbend sensitive, or coatings are hard to strip, or some other problems. These telecom grade coatings are not great at elevated temperatures. So we observe the degradation, the coating becomes liquidy in nitrogen. The best coatings at harsh conditions, the absolute winners in this series of testing are coatings with silicone primary and high temperature acrylate layers. And there are a few other coatings, DA5 and SA4, which perform pretty well at elevated temperatures and in harsh conditions. Now, do we see any clear winner in all types of testing? Is there an ideal coating? No, there are no ideal coatings, unfortunately. We indeed sacrifice something if we want to modify the telecom grade coatings. Then it has some deficiencies at ambient temperatures and maybe also at low temperatures. For us, this comparison is very important because we make optical fibers, and knowing the performance of the coatings, we can have this in mind if a customer is approaching us and explaining a specific application of the optical fiber. Then we can select the best coating for this particular application from this list. And this brings me to the conclusions. First of all, telecom grade coatings are optimized for use at temperatures around 23 to 85 degrees C or lower, but tend to fail at elevated temperatures and other harsh conditions. Silicone acrylate dual coatings display the best performance overall at elevated temperatures and exhibit high resistance to water. They are the best coatings, at least within this series of testing, for some mid-temperature applications, for instance. If we take overall the ambient temperature and harsh performance of the fibers, then there are single-coat SA2 and SA3, which we consider to be the second in performance. They sustain well high temperatures, but they are sensitive to moisture. That is their deficiency. And once again, per our TGA lifetime criterion, there is a limitation for the upper use temperatures of acrylate-based coatings. Even the best coatings cannot be continuously used above 130 degrees C. At shorter use times, however, the coated fibers can survive much higher temperatures. So once again, it is a big room for speculations, depending on the failure criterion, depending on the usage time. We can say that the same coating is good up to 130 degrees C or 300 degrees C. And here we should put in the data sheet what the test was used for getting this particular number. Once again, 85 degrees C is the rating for telecom grade coatings. If we believe in this rating, then we should believe that the highest upper use temperature for acrylate-based chemistries is probably about 130 degrees C. If we want something with higher temperatures, then we probably should use a different chemistry, like, for instance, polyimides. I wish to thank many colleagues that took part in this work and also my co-authors, which were listed in the very first slide. And thank you very much for your attention.
And thank you, Andrei. And at this time, we will ask as many questions from the attendees as time permits. Starting with this first question, most applications choose acrylate-coated fibers. Why would silicone, polyimide, or hybrid coatings be used instead of an acrylate on the fiber? Or is acrylate always part of the coating matrix?
Okay, acrylate doesn't have to be necessarily the coating material for optical fibers. Polyimides probably are the best coatings if we consider applications at harsh conditions, for instance, like conditions downhole. Also, an advantage of polyimides is that they are very hard, and so you can apply a polyimide in a very thin layer, like only 15 microns will be enough, and the acrylic coating thickness typically is 60 microns. So another advantage of polyimide that it is thin. So for some medical applications, polyimide-coated fibers are used just because they are thinner than acrylate-coated fibers. No, acrylate coatings do not have to be necessarily used, but their clear advantage is that they're UV curable. So polyimide-coated fibers have a polyimide coating which is thermally curable. Such fibers can be drawn very, very slowly, which brings up the price for such fibers. And the acrylate-coated fibers have these UV curable coatings, and such fibers can be drawn very, very fast on draw towers, which brings down the cost of these fibers, and that's why acrylic-coated fibers, which are not specialty fibers but telecom-grade fibers, are very cheap. I hope I answered your question.
Okay. Next. Is urethane just another fiber coating option, or is urethane used in addition to the other fiber coatings?
Urethane is a part of oligomers, sometimes part of monomers, but mostly oligomers. If the formulation doesn't have urethane and if the oligomer molecules are not long enough, then such formulation is low in viscosity. We need, for practical purposes, achieve a certain viscosity level so that we draw the fiber more easily on draw towers. And that's why chemists used to add urethane as a part of these oligomers, because urethane bonds neighboring molecules with hydrogen bonds, and this hydrogen bonding affects the viscosity. Viscosity becomes higher, and that is the main purpose of using urethane, at least as much as I know. But yes, they are always a part of oligomers, but their presence is not 100% necessary. If we increase the length of the oligomers molecules, then we will increase this way the viscosity of the formulation, and we can make something without using urethane, and some of the commercially available formulations that we got do not have this urethane.
Okay. Thank you. Next, in regards to the polymer coatings, which polyimides are typically used? And then as a follow-on, and why are polyimides chosen for this application?
There are several manufacturers of the polyimides that can be used as optical fibers. So polyimides were initially developed as not for applications in optical fibers. They are coatings, for instance, to be used for microchips. And over time, they were adopted by optical fiber engineers. So there are many grades of polyimides that can be used, but once again, I would say that applying a polyimide coating is a very complicated process if we compare it with applying an acrylate coating. So the polyimide coated fibers are, that's why, much more expensive and always considered as a specialty fibers, while with acrylate coatings we may have specialty fibers, but we may also have commodity telecom fibers. I hope I answered this question too.
Okay, thank you. Next, do you feel that the test methods you selected for the different failure modes cover most of the hazardous applications for optical fiber cable?
Yes and no. So they cover some probably significant part of the applications. For instance, if a fiber is used in water or in cable gel. But we know that there are some applications where the fiber is used in another environment, for instance, in mineral oil or in a type of an alcohol, or somewhere it is in contact, for instance, with the metal. And each specific application and each specific system deserve a special investigation. And once again, if we have a different environment, you will have somewhat different behavior of the fiber. And for instance, the upper use temperature for a fiber which is used in water will be different from the same upper use temperature if the fiber used in a cable gel or in air or in nitrogen environment. So that finishes my answer. Yeah.
Thank you. Next, some companies are claiming 150 degrees C and 180 degrees C ratings for acrylate-coated fiber. What is your view of the validity of these claims?
Okay, these numbers are incorrect if we consider that 85 degrees C is the official rating of the telecom-grade fibers. So these numbers, I'm sure, were obtained by applying some experimentation. For instance, thermal cycling of the fibers can be done up to 180 degrees C, or maybe some aging for a month, but probably not for 20 years. But also, we can say, okay, everything depends on specific application. There may be some application where even a fiber without a coating can be used continuously for 20 years if we do not touch this fiber, for instance. Anyway, if we have an honest comparison between different manufacturers of optical fibers, we should say if it is an acrylate coating, most likely it can be continuously, 20 years used up to 130 degrees C and not higher.
Okay. Thank you. The next question I will ask, so which polyimides are typically used? I understand there are many types, and that's why a previous question was asked.
Okay, so that is sort of a sensitive information for all of the manufacturers of optical fibers, what exactly are the grades of polyimides and the process. So if there is a specific question, probably it's better to contact me by email.
Okay, that's clear, and as you will be told, the contact information will be provided. At this point, I am seeing no more further questions, so I would like to thank you, Andrei, at this time.
You're very welcome.
For presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Andrei after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, July 21st at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 65 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 8th through Wednesday, October 11th, 2017, at the Gaylord Palms in Orlando, Florida, USA. In addition, the second annual regional UL and IWCS China 2018 Cable and Connectivity Symposium will take place on Monday, March 19th through Thursday, March 22nd, 2018, at the Pudong International Convention Center in Shanghai, China. Please visit our IWCS website at www.iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.